So as we're looking at applications of the Maxwell's equation, this time I'd like to turn my attention to a more practical application. In the next video, we will be talking about a device called a transformer, which takes advantage of Faraday's law of induction. Now, this is particularly useful for being able to transmit AC electricity. And so I'd like to take this video to introduce AC electricity and set the stage before we get to the transformer in the next video. So first off, just defining terms. So far, all the circuits we've been looking at are what are called DC circuits. Now this stands for direct current, which means that current flows in one direction only. AC stands for alternating current. So here, this means that the current flows back and forth in an oscillatory manner. Now, within the physics community, these terms AC and DC have taken on a bigger meaning than just merely direct current and alternating current. A lot of physicists will refer to something as, say, having a DC contribution when they just mean that there's something steady going on, or that there's an AC contribution because there's something oscillatory happening. But here we're going to focus on just purely in electricity. So what's the big deal with AC? For commercial power transmission, although with the advent of solar panels, things are going to changing a bit, but within the context of commercial transmission, it is much easier to run a motor in AC than DC. And if you think about it, you look at a lot of factories, assembly lines are nothing but motors after motors after motors after motors. So if it's easier to run a motor in AC, that is a much better choice. The second issue is that AC allows for a device called a transformer. Allows for the use of transformers. And in the next video, what we'll see is this allows for minimizing heat losses in transmission lines. To date, when we've been looking at transmitting electricity, the typical lengths of wires that we've been using could be measured in centimeters. If you're the power company, your transmission line runs can be hundreds or even thousands of kilometers long. And the internal resistance, the small resistance that we would have with the wires, when the wires are that long, it's not negligible anymore. And in fact, if you are familiar with the history of the War of the Currents, Edison was a proponent of DC power transmission. And basically the voltage sag that you would get due to the internal resistance of the transmission lines was so great that he found that you basically wouldn't be able to profitably or even usefully run a power line for more than about 2 city blocks. So he envisioned just having really small power plants every few blocks, taking care of about a 2 city block radius. Tesla and Westinghouse, upon developing AC, with the use of the transformer, you could greatly reduce the currents that were going through the wires. And so instead of having to run power, instead of being only able to run power a couple blocks, you can run it thousands of kilometers. This is especially useful if you want to, say, bring electrical service to a rural area. When farms are spaced more than a couple typical city blocks, you would be basically, in Edison's scheme, basically needing a power generation plant, more or less at each and every farm, which wasn't going to happen. So those are the big advantages of AC. Now, it turns out that DC is making a bit of a comeback, both because solar panels are DC generation, whereas most other forms of generators we saw were, when we saw electrical generators before, they were generally AC generation. And also there has been some advances in transmission line development, but that allow for DC, and I'll get into that in the next video as well. All right, so since the current is going to be sloshing back and forth in an oscillatory manner, we'll be describing the EMF here. If you just plot it as a function, it's usually set up to oscillate, say, as a cosine, for instance. So the EMF will be the maximum EMF times cosine omega t, where omega is 2 pi times the frequency of oscillation. So this period here, remember, is going to be 1 over the oscillation frequency. This remember, this is a script capital E for EMF. Will be oscillating between plus and minus a maximum EMF. Now, strictly speaking, you should be writing parenthesis T parenthesis here, but in AC, since everything, we understand that everything is going to be oscillating as a function of time, we just don't bother writing the of time. So if we're talking power transmission, there are 2 main frequencies that are used depending where you are in the world. If you are primarily in the New World, and there are exceptions in both cases, most of the New World has the frequency going at 60 hertz. And there are some countries that don't and use 50. And in most of the Old World, but again, there are exceptions, most countries in the Old World do 50 hertz, and the exception, and the countries that are an exception, do 60. So just very roughly, it's either going to be 50 or 60 hertz, depending where in the world you are. Why those numbers? Well, it turns out that for efficient operation, the frequency needs to be somewhere around there. So 50 is half of 100. That goes a long ways to making math easy. And 60 just follows along with the idea that there is 60 minutes in an hour and 60 seconds in a minute. So why not have 60 cycles per second for your electricity? Just take it one more 60 down. And we can thank the Babylonians for that when they decided to do all of our time measurements in base 60. And we've been doing that ever since. So either we just keep rolling with the 60s, or you say that 50 is half 100. That was basically the logic behind those choices. Now, if you're talking something other than power transmission, we'll just say within devices. Frequencies will range from about 100 hertz up to about 1 billion hertz, or 1 gigahertz ish. All right. So let's start to think about what will happen if you apply an AC source across a load. And so here we'll go back to thinking about a toaster. So the symbol for an AC source is just a circle with a little sine wave in it. So this is our AC source. That'll be equal to the EMF. And a toaster is literally just a resistor. So this is a good commercial application here. So we got a resistor here. Now what's going to be happening is the voltage across the resistor is going to be constantly changing polarity because the source is constantly changing polarity. And what this also means is that the current is going back and forth as well. Now you'll notice I wrote that with a lowercase I. So the convention here is that if we're referring to the instantaneous voltage, you use a lowercase v, and that will be equal to the whatever the maximum voltage across the resistor is times cosine of omega t. And the instantaneous current through the resistor will be whatever the maximum resistance is times, so maximum current is times the cosine of omega t. So again here, this is just, if we look at this over here, our lowercase v of r is just really saying the voltage across the resistor as a function of time, and our lowercase I of r is just shorthand for saying the current through the resistor as a function of time. And that is very common notation. So we can go ahead and write Kirchhoff's loop rule still, and write that the EMF minus IR equals 0, and that will be true at all times. Or we can say it's the EMF minus the voltage across the resistor is equal to 0 by twinkle twinkle little star delta V equals I times R, because Ohm's law is still applicable for resistors. In fact, if we simultaneously plot both the voltage and the current, so I'm going to plot two things at once. Let's just do it over one period here. So there's the time. We'll go ahead and plot our voltage in green. And we'll go ahead and plot our current in purple. There we go. So the voltage will go back and forth between some maximum value, plus and minus VR. So it's going like a cosine here. And since by Ohm's law, the current through the resistor is always proportional to the voltage across the resistor, you can say that the current going through the resistor will go back and forth between plus and minus some maximum current. And this will just follow the exact same shape. Now, I've drawn these at different heights, but keep in mind that the voltage is in volts and the current is in amps. So literally the scale I choose to draw either of these is completely meaningless. I could have drawn the current bigger than the voltage, and that wouldn't mean anything because the units don't match. But what we see is that that the instantaneous voltage and the instantaneous current are always in phase. Now, for capacitors and inductors, as we get into future videos, we'll see that that's different. Alrighty. So, although we can talk about oscillating back and forth with as a function of time, for most practical applications, what we're interested in is the average behavior. So if I plot the current as a function of time, say looking something like that. Actually, let's do 2 cycles. There we go. There we go. If it's going through a toaster or an old style incandescent light bulb or something like that, what's happening is the power being dissipated at any instant is going to go as the square of the current. So if I plot the power being dissipated by our resistive load, we'll be going from our maximum current squared R down to 0, and we don't need to go to the negative side because we're going to be squaring. So what that means is that it's going to look something like this. If I can, oops, if I can draw it right. Goes down to 0 there, max there, 0 there, max there, 0 there, max there, 0 there, max there, 0 there. So if you're in the new world where the current is oscillating at 60 cycles per second, which means 1 back and 1/4 every 60th of a second. So this period would be 1/60th of a second in the new world, 1/50th of a second in the old world. Your toaster emits 2 pulses of light, or your old incandescent light bulb emits 2 pulses of light, so forth. So either like 2 blasts of heat from the toaster, 2 pulses of light from the light bulb, whatever. Now this is happening fast enough that you don't particularly notice that your toaster is flickering. So it's be more useful if we could describe some average behavior. And we've already seen this before. This is going as cosine squared of omega t. And we saw that the time average of cosine squared omega t is 1/2 of this. So the power is going to be 1/2 of what our maximum is times R. And so here I just want to be clear that this is a max current there. All right. So what's usually done is we define what's called the RMS current and the RMS voltage. And they're defined in exact analog to when we were doing RMS velocities in thermodynamics. And it turns out that you can show that the square, which is the square root of the average of the square of the value. And so you can show that the RMS current, which you usually just write I without any subscript at all, will be equal to your maximum. So again, I'm just noting that that's a max value here over the square root of 2. And similarly, the voltage, which we usually don't bother writing the RMS subscript, will be the maximum voltage. And again, I'm just observing that that's the maximum voltage we have over root 2. So by doing that, we can go ahead and still write P equals I squared R, and that is correct. But this is using the RMS value. So again, if we don't write a subscript, what we mean is the RMS value. And what this will let you do is, with one exception, this will let you write every DC equation you know. You can write them with the RMS values and they still work. This turns out to be the correct way to write power. To use things like I times V, we'll have to modify that. That will be coming in a future video. But that's only the case if there's more than just a resistor involved. So when you do things like buy a light bulb or something like that, well, first off, now it's going to be a compact fluorescent bulb or a LED bulb that will be rated according to what an old style incandescent bulb would do. But let's just assume you still have an old incandescent bulb kicking around. Let's say you have what was labeled as a 60 watt bulb. What this means is that the power being delivered by a 60 watt bulb, when plugged into a socket of known voltage, the power will be 60 watts when plugged into a socket of a known voltage. So let's go with North America here, where our RMS voltage would be 120 volts. So what's going to be let's find what our RMS current would be and what our maximum voltage and current would, and our maximum voltage and current. So first, let's go and find the RMS current. Because this is a purely resistive circuit, we can get away with writing that the average power is equal to I times V here. So if there were an inductor or a capacitor in there, we wouldn't be able to do that. But for a purely resistive circuit, this is still okay. So the current will be equal to the power over the voltage. So this will be 60 watts over 120 volts, means it pulls half an amp RMS. And we can even use this to go ahead and figure out what the resistance would be. It's still going to be true that the voltage is equal to the current times the resistance. So the resistance will be equal to the voltage over the current. So this is 120 volts over half an amp is 240 ohms. So in North America, if you buy a 60 watt bulb, What they're telling you is the resistance of the bulb is 240 ohms. Now, if you go and plug this into a European outlet where the voltage is 240 volts, it will dissipate 4 times the energy. So it would really be a 240 watt bulb there, and it would probably burn out in almost no time. All right, so let's go ahead and find those maximum values. So the maximum current would be equal to √2 times the RMS current. So this will be √2 times half an amp. It's going to be 0.707 amps. And the maximum voltage that we're oscillating back and forth across will be √2 times the RMS voltage. So it's √2 times 120 volts is 170 volts. So when someone says, I have a 120 volt AC circuit, what they mean is that the voltage is oscillating back and forth between plus 170 and minus 170. And by the same token, if they say it's a 240 volt circuit, they mean that the potential difference across the leads is oscillating between plus 340 and minus 340. Okay, so in the next video, we will introduce the transformer and discuss electrical power transmission. Catch you over there.